Thank you. So, oh, I don't have to. I don't know. It's on your computer. Yeah. Thank you. Very good. So thank you so much, Chris. It's really nice to be back here at Texas A&M. What I'm going to talk about today is based on a. Oh, no, it's not working. All right. Yes, very good. It's based on a set of work, on a set of papers that I worked on in collaborations with these fantastic people, Lam Hui at Columbia, Austin Joyce at the University of Chicago, Lucas Antoni at the ICTP in Trieste, and Adam Solomon, a former postdoc at CMU, now at McMaster. Okay? So this is very much still a work in progress, so much so that we have a paper that is hopefully going to come out within the next couple of weeks. And so some of what I'm going to talk about today also covers this work that should appear very soon. Okay? Now, the starting point for this work is a very interesting observation, namely the fact that black hole solutions in 4 dimensions in general relativity are macroscopic objects that display no static linear response whatsoever. In fact, as far as I know, these are the only macroscopic objects that we are aware of in nature that have this property. And depending on how familiar you are with this statement at this point, you might be asking yourselves a different set of questions. If you've never heard of these, you might be asking how so? How can we show this? Where does this statement come from? If you have seen the derivation, perhaps you might be asking, well, okay, so what? I do a calculation, I get 0. Why is that such a remarkable fact? Finally, if you know why it's remarkable, you might be interested in understanding, okay, then why is the fundamental explanation for, what is the fundamental explanation for this result? Okay. And so these 3 questions also form the outline for at least most of my talk today. Then depending on how far we get, I'll also discuss a few more things, but I don't want to rush through the material. So if at any point you have any questions, please feel free to stop me. I'd rather this be a conversation than just me talking for an hour. Okay. So let's start trying to answer the first question. How so? How is it that, how do we know, why do we say that black holes have no static linear response? And to start, I would like to begin with a warm-up example, which is very much a textbook example, so much so that I stole this picture from Jackson. And the warm-up example is that of a dielectric sphere, in an external constant electric field. Okay. The idea here is that if your sphere has some dielectric properties, then the sphere will get polarized. The amount of polarization will depend on the strength of your external electric field. And the way we would go about solving this problem is to look for a solution to the Laplace equation for the scalar potential. We can use the fact that the system has azimuthal symmetry, rotations around the direction of the electric field, to know already that the potential is going to meet an expansion in Legendre polynomials. And then solving this problem just amounts to, oops, sorry, I was told I shouldn't walk that far, amounts to finding a solution for these coefficient AL and BL. And of course, to find a unique solution, we got to know what the boundary conditions are. And in this case, the boundary conditions are that at infinity, the potential should be just the potential of a constant electric field in the z direction. At the interface with the sphere, the tangential component of the electric field and the normal one of the displacement should be continuous. And because there is nothing special at the origin, the potential should remain finite at the origin. And these boundary conditions uniquely specify your solution, which takes this form. So it just contains a first order Legendre polynomial. And there are actually, probably this is not a result that, it's something that you guys have already seen many times, but it's a good toy model for what I'm going to discuss next. So let me just make a few comments about this. So first of all, what I'm calling epsilon r is the relative dielectric constant. Okay. We are able to find an exact solution in this case because electromagnetism, of course, is a linear theory. And in this solution, there is a growing part that grows like R, which is the one essentially responsible for that recovers the external electric field. And there is a decaying part that goes like 1 over R squared that captures the response of the sphere. Okay. And of course, the response is proportional to epsilon, to E naught, which is the strength of the external electric field. This makes sense. So the response by itself is not a property of the object, meaning just this magnitude here. The response is a property of the object, which is the ratio between the induced dipole in this case, because we have something that goes like 1 over R squared, and the magnitude of the field that you place your sphere in. Okay? That ratio only depends on properties of the sphere, in this case, the dielectric constant and the radius A of the sphere. And it's something that we could have actually just guessed based on dimensional analysis. Okay? The response, as I defined it, is something that has units of length cubed, and the only length scale in the game here is the radius of the sphere. So it's gonna be some factor of order 1 times A cubed. Okay. Now, last comment, again, because this is all linear, the modes with different angular momentum L decouples from each other. We've placed our sphere in an electric field that only had an L equal 1 mode, and therefore the response that we get is only a dipole, only an L equal 1 type of dipole. Okay? So all these features now are features that we're going to see again in the case of black holes, just some of the solutions are going to be more complicated, but the basics physics is exactly the same. Okay? So imagine now that we take a black hole rather than an electric sphere and we place it in an external scalar field. And we want to know how does this black hole respond to that. So what we would do now is solve the static form of, imagine this is a free field. So we would solve box phi on a Schwarzschild background in the static limit. And the type of solutions that we would find would look like so, okay? They would be the general solution for any fixed angular momentum number. It's going to be a linear superposition of 2 hypergeometric functions, essentially, up to this factor of 1 over R to the L plus 1 in front. Okay? Now, the first hypergeometric function actually is just a scary way of writing something that is much more benign. Meaning that the first hypergeometric function is just a polynomial of nth order in R over Rs. Okay? Nothing more special than that. Now, the boundary conditions that we want to impose now to solve this equation are that at infinity, we want our scalar to essentially recover the external field that we're placing our black hole in. And so for a given angular momentum number, say L, we want our scalar essentially to grow like R to the L. And we will demand that at the horizon, our scalar remains finite, so that nothing funky, no singularities take place at the horizon. Okay? These are the boundary conditions that we will impose. And when we do that, we find that this second hypergeometric function must just not be there in order for our solution to remain finite at the horizon. And so all the BL coefficients must be 0. And because of how I define the, yes?
So you're not imposing any condition at similarity, R is equal to 0.
No. I'm just doing everything outside the horizon all the way up to horizon.
Okay.
Yeah. Now, the way we define the response is exactly how we defined it for a dielectric sphere. Namely, we take the ratio of the coefficient of the piece that goes like an inverse power of R, and we divide it by the coefficient of the growing power of R. Now, if we keep only the first piece, we clearly have a growing power of R, like R to the L. But this is a finite polynomial that stops and doesn't contain any inverse powers of R. So I interpret this as a statement that the response is just 0. And this is the simplest case that shows that for a Schwarzschild black hole, if you place it in an external scalar field, there is no response. But you can extend this result by placing your black hole in an external spin 1 field or spin 2 field, so turning on some gravitational perturbations. And you can consider not just Schwarzschild, but actually a spinning black hole, a Kerr black hole. And this result will remain true. The details might be a bit more complicated, but it will still be true that the response, the static response, is 0. Yes?
So is this something related to no-hair theorems?
In a way, except that for no-hair theorems, if you want, the boundary conditions that we would impose are different. So typically when you look for a solution with a hair, you are looking for a solution where your scalar falls off at infinity, like some powers of R, whereas here we've assumed that there is a growing part.
So far you didn't assume anything about quantum mechanics. You just consider GR, actually.
Yes. So far it's all classical. And now in maybe 10 minutes or so, I will show you that once we view what's happening here from the perspective of effective field theory, then this result is actually quite puzzling. But so far, this is just a statement in classical general relativity.
Especially the second one, because if you're a firewall believer, then you're saying that the second one is wrong.
The second hypothesis. Yeah. So I think in the standard approach, at least in general relativity, is that at the horizon, all scalars should remain finite. We know that the richest scalar should, in particular in vacuum, should even vanish, and all other scalars we assume should be finite. So it's, yeah, you could say that it's an assumption, but it's a fairly widespread one, I would say. A fairly common one.
What about the ADS Schwarzschild case?
So if we place this in ADS, then it becomes more complicated because now your follow-ups at infinity are going to be different, right? You're not going to have any more a decaying and a growing mode like this necessarily. And so now we need to understand how we would define the response in that case. So I think it's not as clear-cut as it is in flat space.
And also you have kind of a boundary in the infinity, and then you have a superposition of incoming and outgoing ADS situation.
Yeah, so I think there, what we mean by static response is a little less clear-cut than it is here. And so depending on how you define what you mean by response, you can get different results. Whereas I think, yeah, at least as long as we stick with the flat case, I think there is no ambiguity. Okay, let me also maybe try to visualize what's going on in a more pictorial way. Okay, so you could imagine trying to solve the equation for a scalar close to the horizon or at infinity. And in an asymptotic form, you would find different independent solutions. At infinity, we saw you would find either a growing mode or a decaying mode. Whereas close to the horizon, you would find something that blows up or something that remains finite as your independent solutions. And if you want, the question based on the boundary conditions that are imposed is how these two set of independent solutions are connected to each other. And generically, you would expect that if you start with one particular solution at infinity, you will get an admixture of the other two close to the horizon and vice versa. That would be the generic expectation, right? Whereas what happens actually is something like this, that the growing solution at infinity is connected purely to the finite one near the horizon, and whereas the decaying one is actually a linear combination of the finitely divergent one at the horizon. And this is sort of connected to what you were saying about the Noether theorem. In its simplest form by Bekenstein, the statement that if you demand just a 1 over R solution at infinity, then that is not compatible with having a scalar that remains finite at the horizon. Yeah. Very good. Now, static response is actually non-zero for other objects such as stars. And the reason why that is the case is because a star has a surface at a radius much larger than its Schwarzschild radius. And so when you extrapolate these two solutions at infinity all the way to the surface of the star, both solutions remain finite. And at that point, once you hit the surface of the star, to solve your equations all the way up to R equals 0, you need to take into account the fact that there is matter around and your geometry changes. And so you want to demand what are the two, what is the linear combination precisely that gives you something finite at R equals 0 now. And typically you find a non-trivial linear combination that does the trick. Okay. So this is why for stars or other compact objects, we can have a non-zero response, and the response is actually set by dimensional analysis by the scale, by the radius of the star, our star. Okay, so this is why we claim that black holes have non-zero static response. So let me pause here for a moment before we move to the next part of the talk and ask if there are more questions. Okay. Very good. So, okay, why do we care? Okay, maybe on dimensional analysis, you would have expected the response to be set by the scale of the problem, which is the Schwarzschild radius. That would have been our naive expectation. But that's why we do calculations in physics, because sometimes our expectations are naive, and you got to do a calculation to see to figure out what the right answer is, right? But what I would try to show is that actually this can be viewed as a naturalness problem when you think of black holes in a more effective field theory viewpoint. Okay. And to do that, let me now consider a black hole at scales much larger than its Schwarzschild radius, okay, in a limit where I can actually forget about the detailed nature of the black hole and approximate it at a first pass as just a point particle interacting with some external field. So at these scales, the physics, the dynamics must be described by an effective theory that only contains the light or the gapless degree of freedom in the system, which are, say, my massless scalar that is interacting with the point like now black hole. It could be the gravitational perturbations, and the other important gapless modes are just the center of mass coordinates of the point particle. Okay. So we could describe what's going on now with an action that contains these ingredients, and that satisfies some symmetries like Poincare invariance. Now our point particle will live in flat space. If it's interacting with a massless scalar, the action must be invariant under shifts of the scalar. And in the simpler case where I consider just a free scalar in Schwarzschild, it should also have a Z2 symmetry, be invariant if I change phi to minus phi. Right? Those are sort of the main constraints. And with these constraints, the type of action that we will write down around Minkowski would look something like so. The first part would be the action for a scalar just in flat space, where I'm allowing for small perturbations around Minkowski of the metric. And then there is
So how about BMS symmetries at infinities?
Very good. So I mean, the standard, how should I put that? The true answer is I'm not sure. So in the sense that in the standard EFT viewpoint, you normally wouldn't necessarily worry about asymptotic symmetries, but more about either global symmetries or local symmetries if they are gauge symmetries, and those would constrain your effective action. It's actually an excellent question. I'm not sure how one would what effect asymptotic symmetries would have on the point particle EFT. It would actually be an interesting thing to explore. I don't know.
And don't you expect the existence of black hole to break the Poincare symmetry somehow? Are you?
Yeah, very good. But that breaking is a spontaneous breaking, right? In the sense that the point particle action, if I forget about interaction with the scalar for now, the point particle action for the degrees of freedom x mu, once I fix coordinate reparametrization, and so I only have really the 3 linear coordinates, that action is invariant under Poincare, but Poincare is non-linearly realized on my degrees of freedom. And that's, so for example, translations shift my coordinates, and boost actually act very non-trivially on the velocity, say, of a relativistic particle. And that is because Poincare invariance is still there, but being spontaneously broken by the fact that the particle picks a preferred position as opposed to another one, in a preferred reference frame, the rest frame, they are realized in a non-trivial way.
So this u mu is the derivative of x mu?
Exactly, it's dx mu d tau. It's the forward velocity of the point particle. So these are the type of terms that we write down. And notice that the point particle actions contain a bunch of other terms that can be viewed from an effective theory viewpoint as coming from the fact that our black hole is not truly point-like. We have integrated out degrees of freedom at a scale of order of the Schwarzschild radius, and there are going to be corrections to the leading order action, that is just m d tau, that are suppressed by this scale, typically. Okay. And if you want, it's the value of these coefficients, lambda 2, lambda 2 prime, and an infinite number of other coefficients that tell me whether what I'm approximating as a point particle is a black hole, a neutron star, it's an orange, so on. To get some intuition about these coefficients that appear in the worldline action, let me just take the limit, the purely flat and static limit, and let me write down the equation of motion for phi, which now is Laplacian of phi sourced by some term that contains a delta function localized at the location of the black hole. I'm assuming that the black hole is not moving, it's just fixed at r equals 0. Okay? Imagine we want to solve this equation, and we want to solve it perturbatively. So we assume a phi that grows linearly with r, so in the spirit of how we discussed so far response. And then we add a perturbation phi, curly phi, and we solve for that. Okay? The curly phi that we find will tell us how the black hole in this point particle approach responds to this background that grows linearly now. Okay. So we plug this in there, we solve for curly phi, and we find something that falls off as 1 over r squared. And the size of the response now is proportional to lambda2, this coupling that appeared in the worldline action. Right? So at least some of these couplings that I've added to the point particle action actually encode the linear static response of black holes. Right? Based on effective theory arguments, we would have expected the size of those couplings to be determined by the size of the black hole, because that's the scale that we've integrated out. But because we've done an explicit calculation before, and we've shown that for a black hole, such 1 over r squared fall off would not be there, this tells us that in the effective theory, lambda2 should actually be 0. Okay? And in fact, not just lambda2, but an infinite number of couplings in the worldline effective action. So the expectation that lambda2 was determined by the Schwarzschild radius was an expectation based on naturalness. And the fact that an explicit calculation tells us that in fact lambda2 should be 0 is in disagreement with that. Now, in physics, we usually, when we write down effective action, if there are terms that are not there in the effective action, is because they are forbidden by symmetries. And so the question is, okay, if it is true that these coefficients and the associated terms shouldn't be there in the effective action for a black hole, as opposed to the effective action for other objects, it must mean that black holes have some additional symmetries that somehow, when we go to the point limit, forbid the existence of these terms. Right? And so the question we asked was, what are these symmetries? Can we find them? Okay. Which takes me to the third part of the talk. But before we go there, I just want to make sure that everyone is rightfully outraged by the fact that these coefficients are 0 and there seems to be a naturalness problem.
So you're saying this coefficient has to be 0 because you want to match it with the conclusion from box phi equal to 0 that you did for Schwarzschild. Exactly.
And so imagine I have solved that equation in the background of a star, I would have actually found a non-zero response. And now the size of the induced dipole in this case is what I would have matched to the lambda2, which now for a star will not be 0. Yeah.
Do you find for a star that the response is getting less and less if the star is getting more and more dense? I mean, is there any sense in which the star result limits to the...
I think there is a discontinuity because there is actually a minimal radius, at least in GR, past which a static spherically symmetric object can be in equilibrium. I think it's something like 9/4 GM, something like that. And so you can't really smoothly squeeze the radius of the star all the way to RS. But as long as you remain in this regime where static solutions are allowed, then you see that parametrically, indeed, the response scales like the radius of the star to the appropriate value. Yeah.
What about the effective action for the curved black hole? Because if you treat that, I mean, if you see it from infinite distance, you just see it as a particle. So yes, the effective action would be same. Very
good. Well, not quite. There are actually more gapless degrees of freedom than the ones I've included so far. The three ones that I've neglected are the Euler angles that describe the instantaneous orientation of the object. So the terms that I wrote down should also be supplemented by terms that involve, if you want, in the limit of small angular velocity, involves all sorts of powers of angular velocity of the star, okay, or of the black hole. But it nonetheless remains true that even for a spinning black hole, an infinite number of couplings in the worldline action should vanish. Yeah. Okay, so to try to derive the symmetries that are responsible for this behavior, what I'm going to do is consider again the case of a scalar on a Schwarzschild background. So start from the microscopic calculation that showed us that the response vanishes. And I will make an approximation known as the near zone approximation, which essentially amounts to the following. Amounts to first focusing on the small frequency limit, so that 1 over omega is parametrically larger than the Schwarzschild radius of the star. And then I will look at the region that is in between the Schwarzschild radius and 1 over omega. So that's what I call the near zone. And in that region, I can approximate the equation for my scalar as follows. Essentially, I can modify the part that depends on omega, and as long as Rs times omega and R times omega are much smaller than 1, the error I'm making is small. Now, the important point is that this is an approximation, but when you take the static limit, which means when omega goes to 0, 1 over omega goes all the way to infinity. And in that case, the near zone essentially covers the whole space. So by working in the near zone, we can actually still make exact statements about the static solutions on a black hole background. Okay. Now, if you take this equation, this approximate equation, and you ask yourself, imagine that this static equation came from a black hole living on some metric, some effective metric. What would the metric look like? What you find is that the metric, that phi would be minimally coupled to this metric. And although it's not completely obvious at first sight, this metric, of course, contains a two-sphere, the second part, but the TR subspace is actually just a portion of two-dimensional anti-de Sitter. Exactly, if you view anti-de Sitter as a hyperboloid in 3D space, it would be the region that is highlighted in yellow here. Okay. Now, because of that, both ADS2 and S2 are two-dimensional maximally symmetric spaces. So they have 3 Killing vectors each. Put them together, it's 6 Killing vectors, as opposed to Schwarzschild, the original Schwarzschild solution that would have the 3 Killing vectors due to isotropy rotations and the 1 due to time translation, so it would only have 4. So that's one advantage. But the other advantage is that because the curvature radii of this ADS2 and this two sphere are exactly the same, the combination of these four-dimensional space is actually conformally flat. And because of that, we have 9 additional conformal Killing vectors. Okay? So a conformal Killing vector is such that when you take the Lie derivative of the metric, you don't get 0, like for a Killing vector, but you get up to a factor in front, again, back the metric. Okay. So these are more symmetries that now we have in this problem, and then we wanna exploit. So let me discuss them a bit. Now the S2 isometries are of course just rotations, the same rotations we had for Schwarzschild, so nothing new to say about that. The ADS2 isometries are associated with these Killing vectors here. And these are the zero spin limit of symmetries that were first written down recently by these authors. Okay. And they used these symmetries in a very clever way to essentially derive by algebraic methods the exact solutions that I showed you earlier on in this talk that involved hypergeometric functions. Okay. Using the fact that the ADS2 isometries, SO2, 1, that group has the same algebra as SL2Rs, and hypergeometric functions form representations of SL2R. Okay. Now, they claimed that because of that, because they were able to derive these exact solutions from these symmetries, this is a symmetry explanation for the vanishing of numbers. And my viewpoint is that that's a bit an overreach of the results for the following reason. One, because, as I said, they use these symmetries to derive the exact solutions. And the nice thing about symmetry arguments is that usually you don't need the full solution. You don't need to do the exact calculation. Otherwise, you're just doing the calculation. Okay? The beauty of symmetries is when we are able to derive some results without actually knowing the full solution. Right? And that was not the case for them. The second point is that because these generators L plus minus contain time in the exponential, when they act on static solution, they give you back solutions that are time dependent. So this means that these symmetries are not just properties of the static solutions, okay? But they connect, in fact, static solutions to solutions that have frequencies of order 1 over Rs, and therefore live outside the regime of validity of the near zone approximation. And finally, the last point is that I try to convey the fact that the mystery of the vanishing of response is actually a mystery in the IR when you think about black holes from an effective theory viewpoint and you treat them as point particles. Right? And in their analysis, they actually didn't have anything to say about how these symmetries behave in the point particle limit, which is where the problem is. That's why I think this is not an answer, an explanation for why there is no naturalness problem. So let's now take a look at the conformal Key vectors that we have. We have 9 of them. 6 of them can be put together in pairs, plus and minus. And then we have the first 3. Now, the 6 at the bottom, actually, I won't have much to say about them for the rest of this talk, because they actually share the same problem that they would take static solutions to solutions that have a frequency of order 1 over Rs. Now, this is not to say that they're completely useless, because, as I said, the previous authors were able to get a lot of mileage from those symmetries. And so it would actually be interesting to understand whether there is more information one can extract out of these. But for the purpose of this talk, I just want to focus on the first 3, because the first 3 don't have any time dependence, don't have any time derivatives. And therefore, they are exact symmetries of the static sector of scalars, in this case, on Schwarzschild black holes. Okay? Even though we derive their existence by passing through a near zone approximation, if you just took the action for a scalar on Schwarzschild and you drop time derivatives, you would find that that action has these symmetries exactly, period. But if I'd started with these, it would have felt a bit mysterious. Where do they come from? How did you find them? Okay? By making this approximation, they sort of come out more natural.
Conformal symmetries or
Sorry?
conformal symmetry. No. You said
So let's recap. I make this near zone approximation. My metric is ADS2 cross S2, and it is conformally flat. And so when I put together these 9 generators with the 6 Key vectors, altogether they do form SO4, 2 algebra. So you have a equivalent of a conformal group of symmetries. And when you take the action for a scalar in the static limit, that 3D action also has essentially a 3D conformal group, where these generators actually become regular killing vectors in the 3D sense now. The interesting thing is that they survive also from the 4D perspective as conformal killing vectors. Very good. Now, as I try to make the case that in the static limit, this near zone metric gives exactly the same static solutions as Schwarzschild. And therefore, transformations generated using these conformal killing vectors, transformations of the scalar, are also going to be exact symmetries of the static sector on Schwarzschild. Okay. This transformation would act like so, where the second term comes from the fact that these are not just regular killing vectors, but they're conformal killing vectors. Okay. And I'd be particularly interested in this one, this J01, J02, and J03. Sorry, let me make sure. Okay. Very good. Now, the interesting thing about these symmetries is that they survive even in the point particle limit. So the limit where you take the Schwarzschild radius and you squeeze it to 0. Right? In that limit, they reduce in more Cartesian coordinates to this form, where you can recognize this as being 3D special conformal transformations for a field with weight 1/2. And so the claim is that now the flat limit of these symmetries, these ones that I wrote here, should be symmetries of the point particle action. And in fact, you can check that all the terms that you would write down that would give rise to a static response in the point particle language are actually not invariant under the special conformal transformation. And therefore, it is this symmetry that forces them to be 0 and give you a 0 response for a black hole. Notice that also these special conformal transformations would be explicitly broken at a scale R star for if your object was not a black hole but was a star. And therefore, it is not surprised that these coefficients lambda 2, lambda 4, and so on have dimensions that are set by the explicit symmetry breaking scale in your problem. This is exactly how any other effective field theory works. If you have some coefficients that would be forbidden by a symmetry, but that symmetry is explicitly broken at a small scale, then those coefficients actually are now allowed to be non-zero, but their size is determined by the explicit symmetry breaking scale. Okay. So exactly the same happens for objects that are not black holes. So far I focused a lot on scalars on Schwarzschild. So let me just say that I did that because that's a simpler case to show where equations don't look as ugly.
I have a question.
Yeah, please.
In your effective action, you mentioned that according to symmetry, lambda 2 and lambda 4 equal to 0.
Yeah.
But I mean, what will be the effective Lagrangian after that? Can you? I mean.
Yeah. So those terms will not be there.
What are terms that could be there?
There are other terms that in the rest frame of the object, for example, would involve time derivatives of the scalar. And those would contribute to dynamical response of the black hole. Okay? So what happens if instead of placing your black hole in a scalar that is perfectly static, you actually have some non-trivial time dependence for your background. Okay? Then your black hole in general will respond to that. And these other couplings that I didn't write down but will be there will actually encode that behavior. Okay, so what about a scalar on Kerr rather than Schwarzschild? Then how you implement the near zero approximation for Kerr is a little less standard. Okay, there are several near zone approximations that have been put forward in the literature. We found one that actually makes the near zone metric for Kerr be still ADS2 cross S2. Even though now the curvature radii are not just RS, but are the square root of, I guess, the geometric mean of the Schwarzschild radius and the horizon radius, the outer horizon. But because the metric is still ADS2 cross S2, then everything that goes through, you still have 15 conformal Key vectors. The difference is that when you go and take the static limit, now only J01 and J23 would be exact symmetries of the static sector of a scalar on Kerr. Whereas the other one are just approximate. But other than that, this J01 is all you need. It's already sufficient to eliminate an infinite number of couplings from the effective action. So the solution to the naturalness problem is still there even for Kerr. I have maybe 10 more minutes, so there are a few more things I want to say, but before we get to that, let me pause again, see if there are more questions. Okay. So you could ask, what about fields other than scalars, spin 1 or spin 2 fields? Okay. We know that the response must be 0 there as well. Can we see that? And we are actually still working on that, but we do have some results that are not quite as developed as for the scalar. But let me tell you what we have. Okay. And so to see what we can say about these other fields, let me first look at the scalar again, but now in angular momentum space. Okay, if I break up my scalar in angular momentum modes, then my static equation of motion takes this form with some differential operator acting on phi L, the nth mode 0. And the J0I symmetries that I showed you before, what they would do in angular momentum space is mix modes with different angular momentum. Okay. So transformation rule would look like so, where D plus and D minus are some differential operators of first order. And for what I want to say, actually, we don't need to write down the explicit form of them. Okay. But what we care about is their algebra with the Hamiltonian operator HL. Their algebra is such that if you take a solution with angular momentum L and you act on it with a D plus, what you get is a solution with angular momentum L plus 1. And similarly, if you act on it with D minus, you get a solution with angular momentum L minus 1. So these are like raising and lowering operators, essentially, where you raise and lower angular momentum. Okay. And while these J0I in angular momentum space are mixing all angular momenta, these D plus and D minus are symmetries that I'm calling vertical ladder symmetries. It's going to become clear why in a moment, that just mix modes with 2 angular momentum. Okay. Now, using with these D plus and D minus, we can also build the following operators. We start with this Q0 seed, which we can show is a symmetry. In a sense, we can show that it commutes with the Hamiltonian with 0 angular momentum. And then by recursively sandwich these Q0 with a D plus and a D minus on each side, we can build other operators QLs that are symmetries of the Hamiltonian with L angular momentum. Yeah.
If you go back to the previous slide, is there a way to see whether this ladder is bounded from below?
So yes, in the following sense that if you start with the L equals 0 level, and you are interested in solutions that are finite at the horizon, then with L equals 0, the finite solution is the constant one. And so if you act with the minus on the constant, you get 0. Okay, so now I've introduced essentially two kinds of operators, this D plus and D minus, and these Qs. And the reason why we call them ladder operators or ladder symmetries is because if you represent for any given L the two independent solutions that you have in this way, then the QL essentially mix solutions at a fixed L, whereas the D plus and D minus move you up and down your ladder of solutions. Now, the nice thing is we can use these ladder symmetries at a fixed L to give an alternative derivation of the result that the response should vanish. Right? So anytime you have a symmetries, Noether theorem tells you that there are going to be some conserved currents. And in angular momentum space, where your coordinates will be T and R, and in the static limit, where you have no time dependence, conservational current is just a statement that the radial derivative of some object should vanish. And for the Lth horizontal symmetry, this object is this particular combination of operators acting on phi's and derivatives and so on. Very good.
Why do you need it squared?
Well, it's just because, yeah. So, of course, if the square is a constant, so is the thing without a square. But it's just because if you would pedantically start with the action for a free scalar and run the Noether theorem, you would get a conserved quantity that is quadratic in phi. But you're right, I could have just used the 1 power. It would do the same. Okay. Very good. So now let's play again a game we already played before. We consider the two sets of independent solutions close to the horizon and at infinity. And without knowing the full solution in between, we can calculate asymptotically what these currents would look like for the various solutions. And what we would find is that the Noether currents would vanish if for a constant solution at the horizon or for a growing solution at infinity, and would be non-zero if your solution blew up at the horizon or if your solution was purely decaying at infinity. Okay. And what this tells you is that if you want to start with a solution that is constant at the horizon, for which J is 0, conservation of current tells you that J is going to be 0 for any R in between, and therefore that at infinity you're only allowed to have a growing power. You cannot have a decaying power. Okay. And this is a statement that you have non-zero response. But notice importantly that it's a true symmetry argument because I didn't need to use the full solution. I didn't have to tell you there is an hypergeometric function for at all R's. I only need to know the asymptotic solutions. There's also a nice interpretation from in the IR, which is the statement that solutions that remain finite at the horizon are actually solutions that are invariant under horizontal symmetries. Whereas solutions that would correspond to a star background would actually break these horizontal symmetries. And in the point particle limit, the worldline interactions that would give rise to a response would break this QL. So now from the perspective of this ladder symmetry, the fact that these operators appear in the IR would be interpreted as being due to the fact that the symmetries is spontaneously broken by the background in the UV. Now, the reason why I introduce us these ladder symmetries is because we actually understand very well how to extend these to higher spin fields. In which case, the linear behavior of perturbations is described, say, around the Kerr spacetime, is described by the Tukowski equation, which is a generalization of the equation that I showed you before for a scalar on Schwarzschild. But it is still true that even for this equation, you can define some ladder operators for any value of the spin and any value of the black hole spin, that you can use them to introduce also some horizontal ladder symmetries. And on top of that, there is a new ladder in spin that is essentially a symmetry of this equation that connects solution for say spin 1 to solutions with spin 2 or spin 0 and so on. And once again, you can use the conserved currents for these horizontal these horizontal ladder symmetries to show that the response is going to vanish, also for fields with spin 1, spin 2, and so on. Now, the reason why this is not fully satisfying is because at this level, these are only symmetries of the equations of motion. And in the IR, I argue that the vanishing of response or static response is a problem that arises at the level of the action. Not all symmetries of equations of motions are symmetries also of the action. And so what we are actually working on right now is trying to understand how to uplift this picture to symmetries of the action for, say, some spin 1 field coupled to a black hole and hopefully we're trying to find a similar geometric understanding for these symmetries also in that case. The last comment I want to make before I conclude, that might be of interest to some of you, is that there is actually a nice analogy between this story and what happens to scalars in the sitter. So if you write down the equations of motion for a free scalar in the sitter, and you stick with the number of spatial dimensions that is even, then there is a phenomenon known as the sitter transparency, which is a statement that if you look at solutions in the very far past, on the very far future, and you start in the very far past with a negative frequency solution, then naively you would have expected that in the very far future, that would correspond to an admixture of the two independent solutions. But in fact, the negative frequency solution remains negative frequency all the way, once you get to the future. And in a paper that is now a couple of years old, Compton and Morrison actually showed that this type of behavior also follows from a very similar ladder structure. And in fact, I'm rewriting history a little bit, because when their paper came out, we realized that this was the structure that we really needed to complete our puzzle and actually understand what was going on, why the static response vanished. Okay? So this was, it's a very beautiful paper, and it was very, very helpful to us. All right, let me stop here. The two main messages is just that once we approximate Schwarzschild in the near zone, there is a set of conformal Key vectors that are responsible for the vanishing of black hole response. And there is an associated structure of ladder symmetries that also provides a complementary viewpoint on that. There are still a few things that we would like to understand, especially when it comes to extending these results to higher spin fields. So that's very much work in progress, but I'll stop here for now and just thank you for your attention.
Yeah. So there was some debate in literature about this zero response for
Kerr.
Kerr.
Yeah.
And I think you touched on it, right? Did you, when you mentioned about the time dependent?
Yeah, exactly. So I think
what it was all about. The debate.
I think so. So I think, of course, everyone agrees for Schwarzschild. The debate was whether for Kerr, as you said, whether they're in particular interested in the love number, so the response to spin 2 perturbations, whether that vanishes or not. And I think that at the core, the issue was how some authors defined static response. If you define it from an IR perspective as those couplings in the point particle effective action, then I think there is no disagreement that those couplings vanish also for Kerr. When you do the UV calculation, so you actually solve the equation on a Kerr background, then it becomes more subtle to understand how you define the static response. And physically, the way of thinking of that is that if you have a spinning black hole and you place it in a static field that has some non-trivial spatial modulation, in the reference frame of the black hole, this static modulation is perceived as a time-dependent perturbation, right? And so you need to be careful about when you define the response about working in the same reference frame as other people are working in, essentially. That's essentially the origin of the subtlety. But I think by now everyone has converged on the fact that if you calculate the same thing, everyone agrees on that.
So if we try to understand from quantum mechanics what kind of insight one can get from your physics on Hawking radiation, let's say.
Very good. Yeah, so there is actually one of my colleagues, Ira Rotzin, and his collaborator, Walter Goldberger, has been working over the last couple of years on extending the point particle effective action to actually capture the effect of Hawking radiation. Now, in order to describe that as spontaneous emission, inevitably you also need to understand how to describe absorption, because the two are tied together. And the way this is done is usually by adding an infinite number of composite operators, so additional degrees of freedom to the worldline action. And these additional degrees of freedom are meant to, these operators are meant to mimic the degrees of freedom at the horizon that you are integrating out when you go to the point particle limit. Actually. Okay. So there are actually these operators are important not just for things like Hawking radiation, but also they play a role already at the classical level. For example, if you're interested in superradiance, which is this process where, say, radiation can be amplified by a spinning object, and the spinning object spins down. Those operators would also give you that physics. Yeah, so what Ira and Walter have done in particular was understanding how to describe from a effective theory point particle viewpoint the effect of different vacua that you could choose in the UV calculation if you really looked at quantum fields on a curved background. Right? But so their work is really interesting, but I would say there is certainly more that needs to be done, right? So, for example, it's not clear to me how one would encode the fact that you would want Hawking radiation to be entangled with some degrees of freedom in the black hole. At this stage, I think it's not clear how to describe that from the effective theory viewpoint, and it would be really interesting to figure it out.
So can I ask a question? I think I missed the punchline that you made it towards the end. So you are saying that this ladder symmetries imply that this lambda2 and those coefficients, they vanish?
So these ladder symmetries imply that if you use this current conservation argument, that a solution that is finite at the horizon has to be connected only to a purely growing solution at infinity. Right. And therefore, there is no 1 over R type fall-off, so the response is 0. Okay. But we don't, because the Tokowski equation doesn't follow from an action, we don't have, we haven't shown that those symmetries are actually symmetries of the action, the static action for a spin-1 field, say on Schwarzschild, for example. So that's what we need to do.
So I mean, how did you construct that current?
So you can construct the current by showing that basically mechanically, by showing that for L equals 0, there is a simple object that would be conserved, basically because, yeah, apologies, I don't know if people on Zoom can see that. Basically, for L equals 0, your equation of motion looks something like so, where you have your field here. And so you can say, aha, this quantity for L equals 0 is actually conserved. And then starting from that, you can build all the other conserved quantities for L non-zero. But notice that these would be linear in your field. So this goes back to Chris's question, where now you'd be working in a conserved quantity that is linear as opposed to quadratic in your field. You can do it, it's all consistent, but what we would like to see is really a symmetry at the level of the action. Because as I said, sometimes equations of motion can have more symmetries. Like the typical example is if you take an action for a free scalar, the equation of motion is Bob phi equals 0, and this equation of motion is invariant under a constant rescaling of phi, but the action that it comes from it does not. And so it's always a, it's not a given. You could have more symmetries at the level of the equation of motion. Now, because of what we know at the scalar level, we think that there needs to be a counterpart of this story at the action level, but we haven't quite figured out the details yet.
But that action cannot contain terms which correspond to that lambda2, the other coefficients, right? Because those terms have to be.
Yeah, those have to be 0. But I guess.
So what sort of terms can you have?
Yeah. So what I'm saying is that we want to figure out what the analog of those J01 and J02 is. So let me go back here. Okay. So the statement here was that if you take a scalar field on Schwarzschild, you take the static limit. Okay, so we are not in the point particle limit yet. These operators are exact symmetries of that action. And what we would like to find is an equivalent statement for spin 1 and spin 2 fields. So in the UV already. And at the level of the action, we don't have that yet. We can only do it at the level of the equation of motion with these ladder symmetries.
And do you have any comments to make about half integer spins?
No, except for the fact that in order to obtain these 1 over R type profiles, usually you want to have you want your fields to be bosons because you want them to be in a you want particles to be able to, you want to have large occupation numbers essentially. to create with these classical fields, and therefore the very definition that I gave of response is not something that I could use for half integer field.
Could you extend this analysis to interior of the black hole? Extend.
Meaning rather than imposing boundary conditions at the horizon.
Right, so you've got the conditions at the surface of the black hole.
Yeah.
Could you do that sort of same analysis?
What
What would you expect?
Well, I guess, so what you want to know is still the response at infinity, but just impose different boundary conditions, not stop at the horizon, for example, or that's a good question. So I would expect the response should still be true. The question would be how do you replace the boundary conditions at the horizon at the interior? I don't know,
But you assume your black hole is just point particles. So how come that's?
in the IR, yes. But there we are restricting ourselves to a regime where we're only focusing on scales much larger than RS. So at that point, even going inside the horizon is out of question. We've already integrated out of scales, right? But I guess from the UV perspective, where you actually solve the full problem for a scalar on a Schwarzschild background, for example, you could say, okay, could I, rather than imposing condition at the horizon, impose conditions somewhere inside? But my feeling is that you end up having to make even more controversial assumptions about the boundary condition inside. Already, demanding the fact that your scalar remains finite at the horizon is perhaps, could be debated. And so the more you go inside the black hole, the more debates are going to be. So we're trying to be as conservative as possible. But yeah, but it's an interesting question. If you know what to impose inside, then you could run the same game and see what you get.
But if you wanted it not to blow up on the horizon,
yeah, I suppose
then you've got the one and only solution.
Yeah.
We've already got, I suppose.
That's right. Yeah.
Then you take your hands off the steering wheel and see what it does inside.
Yeah. Yeah.
Then one may ask you, what is the boundary condition on singularity? Then
yeah, so that's where I was like, I'm not sure I'm willing to go there, but
you do like bases, right? Sort of like you were doing before.
Yeah.
Finite, so reaches finite time, or if it diverges, or
yeah. But in fact, as Chris was saying, you could, if you want, start now at the horizon and say, I want my scalar to be finite there, and then extrapolate and see what you get. At that point, you don't even need to guess. And I don't have a good sense for what will happen actually.
Maybe we should also ask if there is any question from online.
Either happy or very unhappy.
Let's thank the speaker.